Welcome everyone to this talk and tutorial on zfit and hepstats. This tutorial will start out a bit inward maybe, so we won't just go through all the basics of zfit and hepstats and to use all these libraries like in itself. I will talk about zfit a bit, but then we will right away start out with some aspects of zfit that we can just take out. So as a core message, you don't need to use zfit to use zfit. We can just take out some of the aspects. That's a core part of it. So for those of you who have not heard yet about zfit or hepstats, this is a project that's going on since a few years where we try to establish a fitting framework in Python that is capable enough to do high performance physics analysis fits. And the project hereby focuses on two aspects, which is on one hand, we need to be fast and scalable. So we cannot use, let's say, pure Python, we need something more. And what we mostly use there is TensorFlow or JAX in the future. So we need all these frameworks that do some real speed up that come from the machine learning world and that run also on a GPU. So zfit itself is quite performant, runs on a GPU, runs on multiple cores. And the second aspect is to have a well-defined workflow. As you see here, this is basically zfit in a nutshell of 5 parts. zfit consists of building a model, which has quite a strong model building capability, of getting your data, creating a loss function or a cost function, minimize this cost function, and then have a result. And now these 5 parts are maximally independent. So this is a core part. The API of this should be as nice as possible, and it should be as decoupled as possible so that we can just jump in and get out of it again. zfit has the philosophy of we can't do everything anyway, so we need to keep things as accessible and let's say as separated as possible so that anyone can come, customize something, use their own parts, replace some parts of zfit. Now, to give you an idea, hepstats then was built on top of zfit, just using basically these few models here, but it's actually independent. And the whole feature set, if you've never heard of zfit, is basically that you can build quite complicated models, multiple dimension composite model. You can create completely custom models, large, small. You can minimize the likelihood for especially unbind, also extended fits. You can include arbitrary constraints to it. And then if you get your hepstats, you can do S-plots, S-weights. You can compute confidence intervals, limits. You can do significance calculation. That's roughly speaking the whole feature set of it. Now, I will give you an idea of what can this really mean in code, and then we will more focus on a few aspects, mainly about these aspects here, and just go in the later part of the tutorial into how to actually build models and so on, since this is rather new, and this works also with pure Python function. Now, zfit and hepstats, just to give you a small example, would be we have a data set, a typical problem that consists of 2 parts. We have an exponential background here, and we have a small single peak here. But that is maybe a bit too small. Let's see. That's what zfit and hepstats are here for. So, building a likelihood with zfit and minimizing it. This is the whole part that we need to do. We will later on go through that more slowly and look at all these steps here, but roughly we have data, we create parameters, we create a Gaussian exponential, and we create a sum of it, then we create an extended unbind likelihood, we create a minimizer, we minimize that, and then we get our result. And this is it. So this is the whole workflow. This is how zfit usually looks like, how I would say every fit of zfit looks like. Some parts are more complicated and some less, but that's about it. And with these models built, we actually don't even need to minimize. We can, for example, try to find out, okay, if you want to set an upper limit, let's say the signal is too weak for discovery. So we can directly use now hepstats, use an asymptotic calculator, so not toys. We can say over which space to scan, what is our alternative, and then just let it calculate the limits, and then we get them out of here. So that's about how easy it is to build something and to do something, and now we've done already a whole analysis using zfit and hepstats. But before we go deeper into that and what we can do and what we can do with models and what we can do if you don't want to use TensorFlow, we'll first look at a part that is rather new, so generalized, which is the minimization, the API, and the workflow. So this, even if you already heard of zfit, this is quite a new feature. And as that, it also has a few rough edges still. Now, as I said before, you don't need to use zfit to use zfit. But as we've just seen before, was we build the loss and we build everything in zfit, and then we minimize it with zfit. Okay, fine, that works. But we developed now minimizer, loss, and result APIs that can also work with arbitrary functions and anything. Now, what is special about this API is that the loss or the cost function contains everything about the what was to minimize. It contains a function to minimize, it knows about the parameters that it depends on, and it knows about constraints. So this is not for the minimizers. Linear constraint is anything that comes only to the loss. Then we have a minimizer, which is stateless and can be replaced by any other one. All that it does is has one function that just minimizes our loss. And from that out, we get a result after our minimization, which stores all the information about the fit or the minimization itself, and it can also do some uncertainty calculations. This again is decoupled from the minimizer. So these are three steps that we will use. We won't directly need to think about all of these, but this in your mind, if you think how to do that or what can I do, or what can't I do, this is the separation, and this proves out to be quite powerful. So let's start out and just use zfit to minimize a function. What we first do is we just set the autograph mode off and the graph mode off. This means that zfit doesn't rely on TensorFlow. Now we can use pure Python, and it's like any normal Python library. You can forget that there is zfit and then TensorFlow behind the scenes. Now, what we do here is we can just create a small functional problem. Then we set the error def. So what is the error definition, for example, 0.5 for a log likelihood typically, or 1 for a chi-square. If you're aware of the IMINI cost functions, that is pretty much the same interface. And we get some parameters. Then here, what we do is we create a minimizer, and we just say minimizer that minimize this function. And in the end, on that minimized object, so this is the fit result, we can call, for example, Hesse, which calculates the Hessian uncertainties, or we can calculate errors with something like profiling, for example, minus. Here we use minute minus, and then we get the result. Same as we got before when using full zfit. So this may be for some of you who know zfit quite new. We can minimize arbitrary functions, just Python, non-Py sums, nothing special on that. The interface of zfit is intentionally built that way that we can use it more general. Now, seeing that, I would assume that someone of you may have the thought of, well, why do we need more minimizers? Isn't that covered already? And that is a good point, because there are many good minimizers out there. Absolutely. Implementing just a new algorithm or trying to outsmart all the others, that's usually not a good way. There's not so much to do it. So zfit just wraps existing minimizers with the goal of a clean interface and behavior. And even that would need quite some reason why would we wrap them and have a new interface in that. And this is basically because we want to have two essential parts, and that is, some libraries have different choices on that. And one is that you first have the configuration of a minimizer. Whenever you minimize something, an algorithm, be it something like Adam or one of the TensorFlow minimizers, be it something that uses approximate Hessians, be it something that uses trust regions, they all have a ton of configurations. And these should all be in a separate function call, so we can just build our own minimizer and we don't need to care about any other existing minimizers. And then there's the other part, which is the minimization. Every minimizer should have exactly one well-defined method that minimizes a function fully, that is stateless and doesn't change it. And this more functional approach of having just one method that is stateless has quite some advantages if you start decoupling things. So then not depending on a state means that other libraries that use zfit or a minimizer, they always know, okay, I can just call minimize and everything is encapsulated in there. I don't need to do through certain steps. So this means this design choice, this has led to two design choices. On one hand, every minimizer is its own class, and every minimizer has basically one method minimize. So it's an absolutely simple setup, but it led to a few powerful conclusions or API adaptations. Now, to mention, this is not an obvious or a possible choice. For example, iMinit, which you may know is a stateful, so you can massage around the minimization, and you can continue the minimization and so on. This is not directly possible with that, but it can always be encoded. We'll see later on in custom minimizers. And there are other things like SciPy, which mixes both of these functions in one, which then leads a bit to a cluttered interface and a few issues in the docs and very hard to find bugs because every minimizer needs to care about the other thing. And when looking around about all these minimizers, why we start wrapping them is because most of these minimizers, they do not offer the combination of having automatically a gradient, allowing for arbitrary constraints, having the same termination criteria, like SciPy in my minimizer, they have all of the different termination criteria, and that they can do uncertainty estimation. So this is usually if you want to do that by hand, these four things, this is basically always, I think iMinit fulfills most of that. It needs to be done by hand, which is saying we didn't even need to calculate the gradient or something. This is all done automatically. And this is basically the role that zfit minimizers fulfill. They just take care of everything that you don't want to take care explicitly and leverages the power of a minimizer like SciPy to support all the other things like arbitrary constraints or the same termination criteria and uncertainty estimations that we will need in high-entropy physics. So let's have a look at how these minimizers look like and how to use them. So every minimizer takes, in principle, arbitrary arguments to be created, whatever it is. But of course, we try to unify them and just use the common language for the one that are there, which you see here. And here we can create a minimizer of our choice. Feel free to create whichever one you like. They should in principle work. And there are many more. What is interesting is something like PyHEP maybe. Mac users pay attention, this does not install easily, which is another powerful library, or the NLOP library can be used. Now, these minimizers accepts anything that has a function and that takes an array of values to evaluate and that doesn't attribute error depth. Needless to say that if you build your loss with zfit, you automatically have that already. Let's have a look at a small intermezzo here. iMinit, I think, is named by many of these, and it's also wrapped in zfit. Now, what we can do is, we know that iMinit accepts the same functions, right? It uses also these positional arguments of array, and it has an attribute error depth. So we can also just use our exactly same function from before that we just use and minimize the thing with iMinit and the loss that we used before. So that this is the loss, this is a zfit loss now. So we can directly take the loss that we created up here in this more complicated example, which we will later look into it. That we minimized, we can also just pass that directly to iMinit instead of using zfit, because iMinit accepts the same functions as zfit does, or let's say the zfit loss. Yes?
Can you make it a little bit bigger?
Oh, yes. Let me see.
It's on here, thanks. Control plus should work. Yeah.
Yeah, is that better?
Yeah.
Okay, perfect. And otherwise, you can always follow us a notebook on Binder if you click the link or download it for yourself if you want. So we see Minuit directly uses also can use zfit losses without any change. Going back, we've seen how to create a minimizer, and then we talk about the minimize method. So it takes exactly 3 arguments. On one hand, loss, which is the function that it needs to minimize. On the other hand, the parameters, which is information about the parameters, so where to start, and we see here we can give more information actually. And it can take an optional argument, which is a fit result, which is a result from a previous minimization that contains additional information. And these 3 arguments seem to be able to they contain everything that is needed to do all kinds of minimization. Now, what we see here, we can have a bit more fine-grained control. We can either directly use a dictionary that contains additional information, or we can create zfit parameters. For those of you who know it already, that just essentially are the same. They just contain a value, they contain limits, and then use this to minimize our function. Here we have our function again before we use the parameters with more info, either this dictionary or the list here. We can minimize it and we get it. And we see now we use type. We also see that this all looks exactly the same as before, and that is very intentional. So minimizer of minimize is the same as when we used minuit, and the result looks exactly the same when we use minute, just we're using SciPy now. One crucial thing here is though, as you will maybe see, is the EDM here. We have to estimate the distance to minimum. I think this is also familiar to any one of you who has ever used minuit or iminute in zfit or iminute package. And this is one of the challenges as well, because many of these minimizers have different convergence criteria. And that's why they actually take zfit a criteria, which is by default the EDM. This means that if SciPy now converges, sometimes this also converges too early by the standard criteria. If SciPy converges, it means that it converged the same criteria as iminute did. This means done by rerunning it in case it didn't find the minimum and make sure that it's over the estimated distance to the minimum. However, this can also be a completely arbitrary criterion. And this is something, since it's a rather new feature, where we're looking at to add new criterion, because calculating the EDM can be rather expensive, especially if you don't have the proximate hashing calculation. However, with that, we guarantee that whichever you use, NLOpt, SciPy, IPOpt, iminute, they all use the same convergence criteria. And now we come to the last step, which is the fit result. The fit result is something that also exists out in the wild, like the optimized result from SciPy, but zfit is a bit more powerful because it also needs to contain the uncertainty estimations. And these are the flags that the result contains, or some of them, whether it's valid, whether it's what's the minimum value, what are the parameters, on some general information, which is more or less of a free field. We contain always the original message, so in case someone wants to look through it, we don't encapsulate things here. Now to do uncertainty estimation, we can use Hesse. And here zfit has 2 possibilities. On one hand, it can use the exposed Hesse method from iminute, or it can use a custom implementation in pure Python, which is completely independent of iminute. If you now print our result again, we see that these uncertainties have been added here, and we see minuit, Hesse, and Hesse numpy, they agree, luckily, very well. We can also use a different confidence level if you want. We don't need to use the default one. And we can also give a different name. This is just by default, it takes the name of the method, but we can also just we can do another uncertainty estimation at 0.9 confidence level and call it differently. And if you printed that again, we just see all of these errors added. The second method is a prefiling method, which is like minus, and there are 2 again. there is minute minus, which uses the exposed minus method of iminute, and there is zfit error, which uses again a completely independent method that does profiling and yields, though, as you see here, the exact same results. Again, this also supports different confidence levels and so on. So we see now these are the three main steps that you can just use in the wild to minimize something. And it means that we can now leverage any SciPy minimizer and just calculate, because remember what we've done here, this is a SciPy minimizer. So we now just got a minus uncertainty and the Hessian uncertainty on a SciPy minimizer that terminated with the estimate distance to minimum criterion. So we get now everything in there, with actually a function that we didn't specify the gradient for. And we can just change one line of the code, go up, create the different minimizers, and everything runs exactly the same again. That's exactly the intention behind it. Now, what did actually happen here? So the function that we gave to minimize, that pure Python function, is actually wrapped in a simple loss. And the parameters were converted to a zfit parameter if we didn't do that before already. We can see that here, because the result also still calls the loss and the minimizer. And now we get the loss that was created. So a simple loss is just something in zfit that allows easily to wrap a function. These are the parameters. If you say Getparams, you get all the free parameters of that loss. And we could also do the same thing as the minimize did by using the simple loss from zfit and say, this is my function, these are my free parameters, and this is my error definition, which is basically the same. So you can also directly use this to do zfit minimization, or you could also use that directly for iminutes. Now, there is a third argument to minimize, which we didn't talk about, that is the init. Now, these are the parameters that we have now lost. And what we can do is we can now take the output, the result, and use that as an input to a new minimize. So we can chain minimizations. Often you don't need that, but if you want to do first, for example, something more global and then take the result of that or something along the line, or be more precise with the minimizer, this can be used. And the contract is that a minimizer can't just use everything that is contained inside the result, which is maybe not exactly, but it's a good approximation. It's a good starting point for the minimization, and that can help a lot others. So we here create a second minimizer, now a minute, with a tolerance that is a bit higher, lower. We minimize, and we see here, we give the result. As a shortcut, if you just want to say continue this minimization, we can also just call minimize with a fit result, in which case it automatically takes the loss from the result, the parameters from the result, and the information from the result. And we see here we get actually better values here. Now, we go to the last piece of the minimizer tutorial, which is creating a custom minimizer. As the philosophy of zfit goes, it wouldn't be a real zfit feature if there wasn't a straightforward way to just implement your own. Of course, one could just imitate that interface, but zfit provides base classes that do all this heavy lifting. That's the main idea behind it. It has pieces to help you with it, but it shouldn't enforce that you would need it. And this is a minimal example of making a chained minimizer. So we just take here a list of minimizers. And what we do in minimize, this is also another zfit convention. If you want to steer the behavior of a public method, then we need to override the underscore method, minimize, and it has the same, usually same, a call API. And then what we do here is we just say, okay, minimize and minimize. And again, this has surprisingly the exact same interface, and we can just use now our custom minimizer to minimize that, which changes this through these two minimizers together. And we got our result. Again, same standard. We can do uncertainties. We can do whatever we want. Just to mention, if you want to have something more powerful, it was just chaining. There are also useful helpers inside the minimizer class. One is an evaluator, which is like a loss function, but it is a bit easier because it takes care of the maximum iteration and automatically handles that. It takes care of NANs, of the strategy, of callbacks. And there's also a criterion which you should create if you use it, and you can see how that is. So just a few helpers to easily create your own minimizer rapid. So in summary, what we've seen here is zfit offers standardized minimizer interface, and in a way that it decouples the uncertainty estimation and also constraints from the minimization process. This should be an implementation detail behind the scene, but declaring it as a user is decoupled. Currently in zfit, we have MLOps, PyIMinit, IPI, TensorFlow optimizers wrapped, but there can of course be more added. And yeah, it's a bit of a new feature. You can't complain about parameters that already exist, and it can be slow with many parameters if you don't have an hashed approximation, because we just have the EDM criteria. But any inputs or wishes for that are more than welcome. So in case someone has questions on that, then you can see in a Slido maybe. Someone has something specific on this. And otherwise, we continue to get a...
Jonas, how
yes?
about you move the Slido window into the sharing, so that, because there are quite a few questions there.
Yes, I'll do that. Sorry, that was the wrong button.
Since they're both web browser things, you could just put the tab
I can share.
into the other tab. Here, I'll give you a link. Oh,
I've
Ben
got it.
already given you a link.
I've got it here. Okay. All right. So that's a very good question. Yes, whether the parts might factor those out in the standalone projects. Yes, exactly. So then we already do that a bit by, for example, factoring out there's a standalone package zfit physics, which is for any physics functionality. So in the core, we clearly don't want to have that, but we still want to have a place where people can contribute that. And in my mind, there is more of like a zfit models and the zfit minimize part. Also, some parts already naturally factored out, such as HEP stats, which is a different name, it's a different library, and it just uses the interface of zfit. But for example, if you want to do anything confidence interval and such stuff, it's not in zfit already. So yes, this is a very good point. And we also have already a zfit interface and so on, exactly to get that. This is indeed the future plan. For the next question, the checks backend. Yes, so this is something that is, I would say, actively worked on. For example, we also, maybe you're going to see that in the a little bit later on in the talk. For example, what we did was we converted most of the zfit internals and now make it also public, a NumPy-like API to the user. So the TensorFlow NumPy wrapper, but so it means that it's way easier to change the backend. Currently, there are still a few blockers on the road that are not quite clear. So one thing is like global parameters, how to handle that, and how to, yeah, there are just a few things where TensorFlow seems a bit more advanced and features that are a bit missing in checks. But this is, I mean, this is something that we actively work on in the sense of we're quite convinced that the future is checks in the end. But we also have to see how checks really develops and how it interoperates with TensorFlow, because it currently does quite well on that, actually. Okay. Or it goes into a direction of that.
Before the next question, can you zoom in on the screen, just like you did with
sure.
Read the questions?
Of course. Of course. So the question was about the checks backend. To mention though, yeah, no, this is really for the backend. That's okay. Then it was set to minimizer status, but it looks like the Hesse and error computation happens later in a result object with state. That is true. And this is the difference though for, so this is a design question that one could in principle also think, should we return every time a new fit result? Now, the fit result is a bit different from the minimizer. So the minimizer itself is stateless. The fit result in this sense is not. But the fit result, there is no part in this sense which depends on the state, except that you have already calculated things or not. But you cannot, so if you do, if you execute the method, this does never depend on previous executed methods, except that it's maybe a bit faster or not. But if you want to calculate an uncertainty, it will always calculate the uncertainty, and you will always have the same answer because you cannot change the minimum. All you can do is add additional information, so to say, to it, but this does not influence, in this sense, anything else. That's the idea behind it. The next question is, what does EDM refer to here? So the EDM is the estimated distance to minimum, which is a metric to determine how far we are from the minimum, and that iMinute famously uses. And I guess this is something like the gradient times the inverse of the Hessian times the gradient transpose, I think. I'm not entirely sure, but it tries to guess how close it is to the minimum. So the errors and the loss, you say, are not decoupled. If you change from NLL to 2NLL, then the prescription for error calculation needs to change to compensate. So yes, the error calculation and the loss, they are decoupled, as they just talk on public interfaces with each other. Because if you change NLL to 2NLL, you're very welcome to implement that. Then you need to change the error definition of that loss, which every loss has, to 1. And that's all that the error calculation cares about. Basically, it's a function and it's the error definition. So, I mean, these parts, of course, need each other. You can't do error calculation without a loss, but the loss needs 2 parts. It needs to be, callable, basically, and has an error definition. And then, so all the information that is needed is publicly, and they should speak only on public interfaces and minimal interface to each other. And the last question is, can you comment on scalability to include many models like voice-done analysis for physics measurement? Is it robust for many PDFs at once? Yes, that is in principle doable, everything. So this is completely scalable, I think. In the end, it's just a wrapper around other minimizers that tries to bring more stability and uniformity in it. But if you want to do physics analysis with it, then and use PDFs, I mean, you can try it out. And that's, I think, my best suggestion. Try it out and see how it goes. Then maybe you anyway want to use full zfit, which then would lead me to the next part of it. Now, let's see, this is the next tutorial. And these tutorials are also online, so I will rather say a few things about it, but this is rather a fast tutorial since we have already seen most of the parts before. So zfit, as we know, has these 5 parts, and we've seen mostly already the last 3 parts, especially the last 2 parts. Now let's have a look at the other 2, model and data. So data is something in zfit that actually is a very, very small feature. We just define with a space, or like with an axis object, basically what are the limits of it, but rectangular, we want to keep it simple. Then we just load the data inside, and data object in general can't do anything. If you want to do pre-processing, use pandas. If you want to load it from root, you can do it directly with zfit, but it's just a path through for uproot. I mean, use uproot there if you want to histogram. If you want to do anything, then there are enough libraries as we've seen. So zfit doesn't really do anything else with data except of wrapping it into standardized format and knowing about weights. The more interesting part is building the model, which is probably the strongest part of zfit. Now, the model, when talking about the model, we usually mean a PDF, probability density function that is normalized over a specific range. The specific range where it's normalized about is called the norm range. And the whole model is parameterized by parameter objects. This is a design choice, and there are maybe also additional possibilities in the future where you're thinking about that as more functional. A parameter object has a name, a unique one, and has a value, and maybe has some limits. So let's just see how these objects work themselves. We can create a parameter, and this is in this sense a global object. That is, if you change it, then it will change everywhere that we use it. We can also change something like floating or not, which is just a hint where to use it. And then we can create a PDF by using the same observables that we created before for the data and giving our parameters. Now this has a number of dimensions. This has the observables and the space and the norm range, which usually are the same, but in principle we could change the norm range. This is just a default space, which is a good hint of what the PDF usually likes to see. And we have a params attribute which contains the parameterization. So the mu of the PDF is the parameter which is also called mu, and sigma of the PDF is a parameter we call sigma 42. If you just want to, in general, get all the parameters of a PDF, because a PDF, these are the direct parameters. It could also be that we have PDFs of PDFs. Then we have a functionality called Getparams, which returns us all the parameters that a PDF depends on. In this case, of course, mu and sigma, they are the same. But for example, if we would use mu for both mu and sigma, here we create a Gauss, and then say .params. The params will tell us, okay, mu is parameter mu, sigma is the parameter mu, while Getparams will just return us a parameter mu, a set of all the parameters. And this is already a simple way of how you want to share parameters. You just use the same parameter again. Now, a PDF in zfit has a few useful methods, which are main feature. On one hand, they have a PDF function, which returns the PDF value. They have an integrate method, which integrates over the PDF, and a sample method. This is basically the core of any PDF. As you can see here, we just integrate, we get the integral. These things, what we get back here is called tf.tensors. But don't be afraid, this is like a NumPy array. I mean, now with checks and torsion always coming up, they all have their own version of tensors, which are fully compatible usually with NumPy. For example, we can say np.square it, and we get NumPy array back. We can also sample from PDF, or we can use the PDF functionality given our sample. All how we would expect that. Plotting is an aspect that we of course need with PDFs, but it's not really directly available on purpose in zfit, because zfit is only model building and the minimization part, and all the rest is to other libraries. But with libraries like Matplotlib or PyHEP, even this is not a difficult task at all. Now, zfit offers quite a few models that we can choose from: crystal ball, local crystal ball, and also allows to create a custom one. So let's just see an example now with something more realistic, as I asked before as well, on a more complicated PDF that we can have. We could create a mass observable. We can create a few parameters, mu, sigma, and then create a crystal ball function, maybe more realistic for a signal. Then we can create something for the combinatorial background, so an exponential, for example. And we can create a KD, kernel density estimation, just from some partial reconstructed or something. Let's say we just have something where we do not have an analytic shape for, but that we want to model with a kernel density estimation. Now we have the three parts. We have a signal component, modeled by a crystal ball. We have an exponential, background, combinatorial background, and we have kernel density estimation for a part that we take from simulation. Now, the final model will be the combination of the three models, the mixture, or the sum of it, which we can do using the sum PDF. Now, if you do a sum of PDFs, we need 2 fraction, and then the last one is 1 minus the sum of this. Or we could also give all 3, and then we just need to make sure that it doesn't run over something. Now, we can just change the values of these parameters. We can, for example, now create a sample from it just to see how that looks like with slightly different values. So what we see here is the sample that is generated in orange, and in blue it's the sum of the model. So clearly this is not yet fitted. We can also just, a small modification, get all the components here nicely plotted. Now, often we are also interested in the absolute yield of the data set, and for that we can also create an extended PDF. Extended PDFs in zfit are handled in a way that the philosophy is, if a PDF is extended or not, it does not change the behavior of it. So a function won't just give you back something else. The only thing is that if you extend the PDF, there are a few methods available, a few additional functionalities available that will just raise an error if it's not extended. But there's no magic that the PDF scales automatically or something like that. For that, zfit has special methods which are called extended PDF or extended integrate, which is a PDF multiplied by the yield. The yield is what we call usually the amount of points from that species that we expect to see with that PDF. Now, one additional thing is if you have just extended PDFs and we create a sum, for example, then we do not need to tell the fractions automatically will be taken from the yields. And you can do this by creating a new one, which creates a copy or set yield to set yield in place, which is a choice in case the copy doesn't work properly. For example, for a custom model, this can be the case. So there are 2 ways to create that. We can take our model and then create an extended model of it, or we can create the model extended. So for example, we create an extended signal with a signal yield, we create a combinatorial background with the extended background, with the background yield and our trico yield, and then we just create a sum here of all these 3 models. Since all of them are extended, this is fine. And now we come to the more familiar part. We have our data, we have our model built. To the loss that we've seen before, instead of creating an arbitrary loss, we can just use, of course, predefined ones such as an unbinned negative of likelihood, or also an extended negative of likelihood. An extended one takes yields into account, an unbinned one does not.
At this break, I'd like to point out 5-minute warning.
Say again?
5-minute warning.
Oh, yeah, thanks. So the loss contains typically model, data, and all the constraints that we have. And we can also, as before, get all the 3 parameters here. An extended loss is just created with an extended unbinned negative of likelihood for the parameters. So for the minimization, we've seen already many things before, but we can just minimize that. We can fix parameters first. We can say, okay, this is not floating. We can minimize it, same as we've seen before. And we can also then just plot the model. And we can do exactly the same things as we've done before. We get our fit result. We have our parameters. And we can do estimate the uncertainty, exactly the same things that we've already seen. I guess there's not so much to say on that. So, and now after that, we've just now created a model, we composed it, we have use that to minimize it, we can get the result as seen before. And we should not forget that there is HEP stats. Now we can directly use HEP stats with the model that we created up here. We can do confidence intervals, for example, by creating a calculator. There's the asymptotic calculator or the toy calculator. Toy calculator needs a bit more time, but it does properly toys. The asymptotic has some asymptotic assumptions in there. And we can create a parameter of interest array and then get an instance that calculates confidence intervals. And we can calculate the interval of it. The same way we can do S-plots, we can do S-weights, and so on using HEP stats directly together with zfit. Now these are the basics of zfit, and I want to point you to, as we see here, the nice plot. And what I want to point you to is to additional notebooks if you want to continue it. On one hand, you can see there are zfit tutorials available that you find on the page. And on the other hand, there are 2 tutorials which I think are quite relevant. On one hand, this one is about custom models. So if you want to create a custom model, it's as difficult as doing it like that. You can just implement the function and we get a PDF with everything available with integral, sample, probability. Try it out, just implement your own function, see whether you can do it, see whether you can do the same game as before. And you can also do more complicated models such as an angular PDF that we took from an analysis, which is 3-dimensional, contains fits a few angles. And that's as hard as it is to implement it. We just take it and we use things like np.cos, second.sine, which is, Matthew, your question before on moving forward, this is exactly part of this, switching the API to a generalized NumPy API. Also, if you say now, well, okay, you don't want to use setnp, you don't want to use TensorFlow and stuff, you can also just use pure Python. There's a section on that, which tells you how you can wrap it, or you can do this matrix switch, graph mode off, autograph off, and then you can use pure Python, NumPy, Torch, JAX, or interface with any Fortran code, or whatever you want in your model. So models are quite flexible. If you're interested in this part, this is the tutorial for you. And there's another tutorial which shows a more realistic measurement that contains information about constraints, adding it, so Gaussian constraints, for example. This is one way of adding additional information. We also see this is more realistic in terms of signal and background, in using other packages like particle and tap units that play very nicely together with zfit, of course. Or to do simultaneous fits, to add different information from other channels, which is just to show you nothing else than we just create 2 losses and we add them and we have a simultaneous fit. And then everything is again the same. I mean, minimize the loss, something you know already. We just create 2 models and fit it to 2 different data sets. And this goes further with a discovery test in HEPstat, so we can see whether here we fit the rare mode and the resonant mode at the same time, sharing some parameters, whether we actually have a discovery or not using HEPstats. Okay. This was the talk about zfit, tutorial on HEPstats. So let's go to the Slido questions. That's a good question. And because this is something that is since a long time on our list, and we tackled that. Short answer is no, currently not. But this is something that we try to tackle in different ways and had people even working on it. And you can always do it partially. That is not so hard to do, especially because you can just write your own configuration super easy with just having a dictionary or something like that. But there is no out of the box way currently to serialize models. But it's very much something that we try to figure out how to do it in the right way. And I think there are also other projects that do that. I mean, like PyHEP does it very successfully, or I think carpentry and so on. This kind of how to dump and load something that we hope to be really to kind of improve. Yes, so the that's a very good question from Jim with the ordered ticks. Yeah, that is actually more of a it's true. Now all the ticks are ordered and they can be replaced. We just very recently, I think, switched from 3.6 to 3.7. We kept there before the dicts to make it clear the intention on it, but that is more of an old thing. Nice check.
Yeah, same as before. Can you read the questions? Thanks.
Oh, sorry. I'm sorry. Yeah. So, is there also bind NLL? Short answer is no, not yet out of the box. But this is something that we also working on quite a lot, and as Henry also mentioned in his talk about boost histograms, we now boost histograms out and having their nice interface. It's just a matter of time. So we work on that. We have multiple branches actually to get it binned. Though it's quite easy to do a bind. So you can't use that out of the box, but I'll have quite a few colleagues actually would just use it like that, because you can build your model and your PDF with zfit. Then you just write your own loss function, as we've seen in the beginning, which takes a zfit model and binds that and takes the binned data. And then you just use a custom function to minimize that. So unbind NLL, no, the question is unbind NLL a wraparound IMinutes function or something completely different? I think you refer to the cost function of IMinute, right? So no, not at all. This unbind NLL is completely custom implementation. In fact, the IMinute cost functions, I think they are quite new. I think they're like half a year old, and zfit ones are already since years around. Now these are two different ones. And the unbind NLL, actually, I think the goal here is to have more knowledge on things. So, for example, to remove constants, to have gradient information, and so on. So while they have a similar interface, they try to fulfill different needs. And I think the IMinutes cost functions tend to be a bit more lightweight. So you thought about interoperability with zfit or PyHEP-based models? Yes, that's a good question as well. And yes, there are quite a few thoughts around. Actually, with PyHEP, we're also in contact. When we started out, that was one of the first things that we talked to each other, because we both use similar backends, we both use similar projects. But it's also clear that, for example, PyHEP really has a different focus on all these binned models, while zfit focuses more to get unbinned models right. I think interoperability with zfit can be a bit critical, maybe on the loss function, but really having the same models and so on, it's a bit tricky because some design joins are quite different. And with PyHEP, I think as soon as we get something more with bin stuff and stuff, we can see what we can put together there. But we're already we have this in mind and sometimes talk. That's it. But I think it's for the short and maybe the medium future, it's not directly addable, except you create your own function where you just add the two losses or something like that. So the next question is, when implementing a custom PDF, are there mandatory functions that have to be provided besides unnormalized PDF, like the CDF, for instance? Very good point. And the answer is no. So I would say, except you need to specify what are your parameters or write the init, because so that you know what's the dimensionality of your function, every parameter it takes. Let's say init, yes, or say which parameters are, but you don't need to provide the CDF, you don't need to provide the inverse CDF or something like that, which is one of the things of this base class of zfit. They take the heavy lifting. So the normalization behind the scenes is done numerically if you don't provide that. The sampling is done with except reject if you don't provide that. So you just need to implement the unnormalized PDF yourself. You can always implement them. You can register analytic integrals. You can completely override the integrate function. You can completely override the sample function, whatever you want, but by default. Or you can also just directly override the underscore PDF function, which means, you take care of the normalization. If you want that, if you want to cheat your PDF and scale it up or scale it down, you can always do that. but the unnormalized PDF just takes the line shape, and everything else should be done.